Hello class. Now in this lecture we are going to look at the equilibrium of a body on a rough inclined plane subjected to a force acting horizontally. In our past lectures we discussed a number of scenarios involving friction on a body whereby we looked at a friction on an inclined plane. That was one of the introductions connected to this topic, but also we had earlier on looked at a frictional force on a horizontal plane when the force is acting parallel to the horizontal ground, and also when the force is acting at an angle. If you have not viewed those lectures, I'm going to share the links in the description box below. So now in this particular lecture, we are going to be looking at a body on a rough inclined plane, and when it is subjected to a force that is acting horizontally. So we are looking at an inclined plane. We are going to consider a body lying on a rough inclined plane subjected to a force acting horizontally, which keeps it in equilibrium as shown below. So this is the body that we are talking about. So let W be the weight of the body, alpha be the angle with which the inclined plane makes with the horizontal, then R be the normal reaction, nu being the coefficient of friction between the body and the inclined plane, phi being the angle of friction, whereby now nu will equal to tan phi, whereby we have said phi is the angle of friction and therefore nu being the coefficient of friction. So it is also going to show that with a little consideration, the force, when it isn't there, the body will slide down on the plane. So we are looking for the force that is going to hold this body, okay, that is going to hold this body at the point when this body is sliding downwards. And we have to look for two forces. One is the minimum force to keep it in equilibrium when it is at a point of sliding downwards. Another one will be the maximum force that of course will keep it the body, that will keep the body in equilibrium, or the system in equilibrium, when this body is at a point of sliding upwards on the plane. That will be our scenario number 2. So scenario 1 is saying a minimum force, we are calling it P1, okay, which will keep the body in equilibrium when it is at a point of sliding downwards. So considering this body, the system of this body, okay, on the inclined plane, we have a number of forces. We have R1, which is the normal reaction due to this body, and remember this normal reaction is always at an angle of 90 degrees to the plane. Then we also have a component of weight that counterbalances or that produces the normal reaction, and that is W cos alpha. So another resolution will also show that the W sine alpha also points in this direction. Of course, that will be the other component of weight of this body. Then the force applied, we are calling it P1, is going to be horizontal, and it's at an angle of alpha, because when you look at this angle here, it is alternating with this other one, the angle with which the plane makes with the horizontal. So having finished that, you also need to consider that at the point of sliding downwards, the friction force is going to act upwards. So if we are looking at the other side, that this body is going to slide upwards, then the frictional force will act downwards along the plane. So now let's move ahead and analyze our scenario. In this case, the frictional force, which we are calling F1, is equal to nu r1, and it will act upwards as the body is at the point of sliding downwards as shown in the figure. So what about um, how do we get R1, how do we get P? So what we are going to do is to resolve forces along the plane and perpendicular to the plane. Okay, so from there, what we do, case 1, we are resolving the forces along the plane, and we see that if we resolve forces along the plane, we will have to resolve this P back along the plane, and then counterbalance all the system of forces along the plane, and then we will get one equation. Therefore, we'll see that if we move this P1 through an angle alpha, okay, back to the whole to the plane, then we will have P1 cos alpha, which will be facing in that direction. So we have P1 cos alpha. What other force is facing in that direction? Plus F1, okay. Then what other force is acting is W sine alpha is equal to W sine alpha. So that means this P1, if I make it the subject, I will have P1 cos alpha equal to W sine alpha. I take away F1, which is nu R1. So I call that one equation 1, and then I resolve forces perpendicular to the plane. If I resolve forces perpendicular to the plane, then that means I will have a force due to P1, so that will be P1 sine alpha plus W cos alpha should be equal to R1. So we will have R1, which will equal to P1 sine alpha plus W cos alpha. So can I substitute this equation 2 in 1? Yes, because I can substitute for R1 in equation 1. So what does that mean? I will have P1 cos alpha plus nu into R1. Nu into R1, which is here. Okay, let me take it to the other side so that I can do it better. So I take it, so it's equal to W sine alpha minus nu into R1, whereby R1 is P1 sine alpha plus W cos alpha. So I take this P the other side so that I have P1 cos alpha plus nu P1 sine alpha plus the W can remain the other side. So this is going to be W is equal to W sine alpha, then minus nu W cos alpha. So I correct like terms together. I will have P1 into cos alpha plus nu sine alpha is equal to W into sine alpha minus nu cos alpha. So what do? I can divide both sides to get P1, and therefore this will be W into sine alpha minus nu cos alpha divided by cos alpha plus nu sine alpha. So what I'm going to do, I'm going to say, but nu is equal to tan phi, which is the same as sin phi divided by cos phi. So I substitute it in here and get my P1 will therefore equal to W into sin alpha minus sin phi, which is new, out of cos phi. So cos alpha, okay, that is the numerator, then divided by cos alpha plus sin phi, cos phi, then sin alpha. So what does that mean? I'm going to multiply cos phi up and down. So that means I'm going to multiply by cos phi throughout here. Okay, so my P1 will therefore equal to W into sin alpha cos phi minus, okay, minus sin phi cos alpha divided by cos phi, okay, divided by cos alpha cos phi plus sin phi cos phi sin alpha. So I'm going to cancel some because obviously this and that will go, such that I have something like P1 is equal to W into sin alpha cos phi minus sin phi cos alpha. I divide this by cos alpha cos phi plus sin phi sin alpha. But from compound angles, we know mathematically that sine of phi, okay, minus alpha is the same as sine phi, okay. Okay, let me make it the other way around. I make it sine alpha minus phi. So this is sine alpha cos phi minus sine phi cos alpha, okay, and cos alpha minus phi is equal to cos alpha cos phi minus sin alpha sin phi. So therefore, from this equation, P1 will obviously be W into, okay, we know our sin alpha minus phi is equal to this. So I'll multiply this by sine alpha minus phi divided by cos alpha minus phi. So this obviously becomes W tan alpha minus phi. So P1, the minimum force required to keep the body in equilibrium when it is at a point of sliding downwards, will always be W tan alpha minus phi, or W tan phi minus alpha. This is when alpha is greater than phi, and this is when phi is greater than alpha. So that is P1. So that's how you can get that minimum force on an inclined plane when the force is acting horizontally and the body is at a point of sliding downwards along the inclined plane.